Thank you, sorry. So let me start with a quick question. How many of you own some IoT device? Oh, nice, I love this question. And how many of you changed the default credentials for those devices? Nice, I'm very proud of you guys, I have to tell you. Today I'm here to present you our research where we focus on the IoT devices, and we really focus on how we can protect those devices if your credentials got stolen or if you didn't change the default credentials. So at the very beginning, I would like to talk about the Internet of Things in like general. Usually when we talk about IoT devices, what people think about are the home IoT devices. But actually, there is only around 15.5% of all IoT devices that are at homes. There are other big groups of IoT devices which are open to the internet, and they are actually vulnerable. We can, for example, talk about the industrial IoT, which are devices in the factories, or IoT devices in cities, where recently, I think in Zlín, in Czech city here, they implemented those trash bins that can send you an SMS when they are full, actually, so you can empty them. And actually what is, at least for me, the most scary about IoT devices is the IoT in the health industry. Just imagine that you have your pacemaker connected to the internet. So you are actually a walking target for all the attackers from all around the world, you know, that's kind of scary. Well, Internet of Things is here for a long time, more or less, and with the devices we also have a lot of attacks. Probably the most famous one happened back in 2016 when it started spreading. Does anyone of you what malware I'm talking about? Doesn't really look like. It was called Mirai, and it's actually spreading still in the internet. We can still see it in the network everywhere. It's attacking. And the way how Mirai was spreading, it was brute forcing the Telnet devices on ports 23 or 2323 TCP. For this brute force attack, the only thing that the Mirai needed was a list of default credentials. And in the first version of Mirai malware, there were only like 65, 67 default credentials, something like that. And once the devices were infected, then they were involved later in 2016 in a massive DDoS attack against different servers, and actually all those IoT devices were able to take down those servers for a couple of days, like big servers, big companies, you know. Later in 2018, Kaspersky Lab published their statistics from their honeypots that are open to the internet. And it's kind of shocking that more than 75% of all the attacks that they captured on their honeypots are on the Telnet protocol. Well, what the hell is this Telnet thingy? It's an application layer protocol developed 50 years ago in 1969. And back in the days, they didn't really care about any security, so it's unencrypted. You can actually just read the network and you see exactly what the user was typing and what the user was doing. Then there was only about 11.5% of the attacks on the SSH, and all the other ports and protocols that we know, they were only 13% of the attacks. So the Telnet is still here, it's still very popular. And the most popular way of attacking those Telnets, well, it was brute forcing again. It was again a list of default credentials or easy to guess credentials that were used to infect the device. Well, all those informations are kind of old, let's say. 2018 was almost 2 years ago. So do we have any idea of what is going on the internet now, like at the end of 2019? It always takes some time from capturing the data to publishing the data, right? Well, we do have this idea. Back in 2018, in summer, when we started with this research, we started capturing the number of Telnet devices open to the internet from the Shodan service. And we were interested in ports 23 and 2323, which are the two ports that Mirai is using, right? And those are kind of the data. We were capturing from the September of last year, every whole hour we are asking Shodan to give us the number of open Telnet devices at that moment on the internet. Those are the graphs. And as you can see, for almost a year, it was kind of stable. It was going a little bit down in the summer. But then at the beginning of August this year, this happened. And yeah, exactly, we reacted the very same way. And this was rising for, I think, 2.5 weeks or something like that. The number was just going up and up and up and up for both the ports. We had no idea what was going on. Then, in the middle of August, in just like 6 hours, happened this. And from that moment, it was just going back to, let's say, stable state, right? So this was very suspicious and unusual, unexpected. We had no idea what is going on. So we contacted Shodan, and they told us that during the first part of the August, which was also the time when the DevCon was, they were doing some maintenance to their servers. So we are probably capturing something that is not there. So our excitement got lower again because the real data are, well, without the big spike, unfortunately. So there is still a lot of Telnet devices, and the number of devices is kind of stable-ish, let's say. So there must be some other system or some detection tool or something that would tell you that your Telnet device is under attack and what is going on there, right? That makes sense. The Telnet is 50 years old. So we kind of check all the most famous intrusion detection systems that are available, and unfortunately we couldn't find anything. They can only tell you that yes, there is some connection on the Telnet port, but that's it. You have no idea what was going on there. You have no idea if it's attack of some bot or other user or what is going on. So we had this crazy idea. Let's create our own Telnet analyzer. The basic idea was pretty simple. Here we have our IoT device. It can be pretty anything with a Telnet port connected to the internet. So here we have our little fish friend. And this IoT device needs to be connected to internet using some device in your network, usually some router or switch, depends, which is your own, so you can control this device. And any user or attacker or bot or whatever needs to connect to this device in the middle in order to connect to the fishbowl, right? And those clients can have like different intentions, you know, like some of them want to help your little fish friend and some of them want to eat it. And our idea was to detect these behavioral changes and to detect that this little black kitty down there is not the real user or the real admin of the fishbowl, and we just want to stop the connection and like, no, you cannot touch my little fish friend, it's my best friend, sorry. So, task number one, probably the most simple one, was to capture the Telnet traffic. This is our infrastructure, as I said, and since the device in the middle is our own and we can control it, we can also mirror ports, right? And thanks to that, we can capture all the traffic. So we have all the packets from the network. Great, task one, done. Task two, probably the most challenging one, is to actually parse the Telnet packets and the payload. We hoped that there would be some library or something that would provide us some information about the Telnet and could extract all the payload from the Telnet packets, but unfortunately we couldn't find anything. There are libraries that will allow you to create a Telnet protocol, Telnet server, to connect to a Telnet server, to speak Telnet, but nothing will open up the packets and understand what is going on here. And we pretty soon realized why. As I mentioned, Telnet protocol is the application layer, which is like the highest. But since we are capturing all the packets from the network, we cannot only analyze the Telnet. We need to start one layer down. We need to actually start with the TCP protocol. And that's because of actually two things. TCP guarantees you the delivery of all the packets and their order. And this is done by a special number, let's say. It's called the sequence number, which is in the TCP header. And based on this, you can order all the packets. Well, great, so we can analyze the packets. Well, but there are some other issues of the TCP. Some packets can get lost in the network, so they are retransmitted. And some packets are just taking other ways than the others, so they are in a different order. So what we really had to do was to understand the sequence number itself. It's not only telling you the order of the packet, it is telling you the order of each byte that was sent to the network. So based on this idea, we could move from the packet analysis to the byte stream analysis of whatever was the device sending to the network. And what we actually have is something like this, just a bunch of bytes. Now we can move to understanding the Telnet protocol because we have all the bytes. Some of you can probably see that at the beginning, this is the beginning of the communication, there is a lot of FF bytes followed by another F something byte. All those bytes. Those bytes are very well characterized in the Telnet protocol. They are called the negotiation bytes, and their only purpose is to make sure that your computer or your terminal in your computer and the terminal on the server side do use the same options. They are not telling anything about the user who is typing on the keyboard. So we can ignore them. What we are left with is all the data that the user sent to the network, aka all the data or all the bytes that the user typed on the keyboard. Here it's pretty simple. We can split it based on new lines, because every time you work in the command line, you write something, you hit enter to send the command. So we can find all the new lines and we can just split it. Question here, is this also everything that was sent to the server? That was used to interact with the server? The answer is no. And because two reasons. Is anyone in here who has never ever made a typo while typing on the keyboard? Exactly. We are dealing with a human being sitting behind the computer who can make a typo. And for example, here we can see a typo. The user typed 6C, which is letter small l, so it's a command, LL. 7F is backspace, because it's a typo. And then is byte 73, which is small s. So the user wanted to do ls command and did ll instead. So this is what the user typed, but in reality, this was sent to the server. Another reason why we still don't have everything that was sent to the server to interact with it is because we people are kind of lazy. And if something can be done for us, the better, right? And here we can see another bytes that are special, non-printable. And to truly understand those bytes, the first one, the 09, is step. It's tabulator, which is autofilling whatever you are writing right now. And down there, those 2 bytes, it's arrow up, which can be used to scroll through the history. And to get what was really sent to the server, to interact with it, we need to understand what happens right after you hit the tabulator, for example. The idea here is the same, so I will explain it only on the tabulator. Let's imagine that we have a client who wants to create a new folder in the server. So the command he uses is the mkdir, right? The client hits the M. Now the server, to kind of confirm that the M byte was delivered, will echo the byte back, will send it back. Only after it's sent back, you can see it on your screen. So when you are connecting to a server that is far, far away, it can take some time from you typing and seeing the letters. This is the reason you need to wait for the byte to come back. The same happens with the next byte, which is K, and again, it's echoed back. And now the user hits the tab. Well, what is the answer of the server? Is it tab again? Well, if it would be tab, then you would see the cursor to jump, right? As usually when you hit tab, when you write some text. In here, the server understands that you want to autofill, and the server will send you back the rest of the command. So when I go back to what the user typed, Here we can see that the user hit the 09 byte, which is the tabulator, but the user never really write the rest of the command. So to put this all together, we had to understand what the server is telling us back on those special bytes. And actually, once autofilled, it looks like this. So now we have everything that the user sent to the server to understand it. When we transfer it to ASCII, here we can see everything. There is just escape down there, which is not printable, that's why it's like this. But this is not really enough, this is just a list of strings, right? Not really telling us anything. What we want to know is which credentials were used in this communication. Yeah, sure, you typed the credentials at the very beginning, but you can be asked multiple times, right? And here again, we need to understand what is the server doing. The server is asking you for your username, and only in that moment you are typing the username. Then the server asks you for a password, and in that moment you will start typing the password. If it's not correct, you will be asked again. If it's correct, you are in, usually welcomed with some banner or some other special characters that we can detect, and whatever is typed next is the commands. So we can easily split it. Here are the credentials up there, and then we have all the commands. Great, we parse the Telnet payload. The next thing that we use in our method is the typing times. It's kind of like keystroke dynamics technique over the network, let's say. And for each byte that we capture and that we process, we also have the time of capturing this byte in the middle on our devices, on our router. And from all the bytes that the user typed, we are interested in the timings between pressing any two keys. So it can be like between T and E, for example, but also between L and tab, even though the tab is really like nothing, but it's something that the user typed, right? And then from the processed commands, here we are interested in the typing times of the whole command, which is the whole line that you send to the server, and the typing times of the executable first part, the executable program. As a very nice characteristics that we find out during our experiments is the usage of special bytes. In here, we can talk about how many typos you do because you are deleting the characters. We can also talk about how much you are autofilling because you are using arrows up and down or tabulators. But also, for some reason, there are users who, when they are thinking about the next command, they are just pressing new line, just pressing enter. So then you can see a command, and then new line, new line, new line, new line. Command, new line, new line, new line, new line. For some reason, they are doing that. I am one of them. I don't know why I'm doing this. And also the same with escapes. Others have the same behavioral characteristic, but with escape. Then we are interested in the credentials, which credentials were used, and in here we want to know the usernames only, the passwords only, and then the combination of the username and the password. For all three of those, we are capturing the order in which the user is using them and the histogram of those passwords. And for all three of them, we are capturing how the user typed the credentials, because you can make a typo again, and what was actually sent to the server. Something similar with the commands. Here, yeah, we have the commands and the programs, and again, we want to know the order of the commands that you are using, and how you typed it, and what you really sent. And since our method is based on the typing characteristics, we asked our users to type as much as possible, in other words, to create a text file in the server and type something there. So we were kind of forced to also implement a function that would extract all the bytes that belong to the V or the nano program, because the commands inside those programs were messing up with the rest of the program. And last but not least, we also extract some characteristics from the session itself. So what is the typical time that you are logging in? Is it usually in the morning, or is it in the afternoon, or in the night? What day in the week you are logging in? Is it weekend or is it working day? Next, where are you from? Where are you logging from? We know your public IP address, so based on that, we can also say your geolocation. Then we are interested in the duration of the session, in the sense of the time, how many seconds it took, and how much bytes did you send to the server. And then what was the last state of the session? By state, we here mean if you try to log in, if you logged in successfully or not, if you did something on the server or not. How far in the state machine did you get? Great. Now we have all the characteristics, and now let's take a look how our tool really works. So here we have our little fish friend behind the router, where our tool is installed. Now the admin of the profile will come and will create his own admin profile, like this. This profile is then stored and used later. Now when we have a new incoming connection from the admin of the network who just forgot to feed the fish, so he just wants to log in and feed the fish, our tool will create a new profile for this user, for this new connection, compare those two profiles together, and if they are the same, then yeah, sure, do whatever you want, it's your fish. But what if it's a different user? What if it's like other cat? Well, here again, the tool will create a new profile, we will compare the profiles, and since they are not the same, they are different, well, it will just kill the connection and protect the fish and notify the admin about the statistics of what is going on and that you are actually under attack. To compare two profiles, we are using actually only 4 different structures in each profile. First one, the most simple one, is just the number. It can be the length of the session, right? Here it's pretty obvious. You just take the absolute value of their difference and you have the comparison. Next is the IP addresses. Here we have a method that can count how many IP addresses are between you and the IP address in the admin profile. Then we have a list of strings. Here we are using some methods to compare them and find out how similar they are based on the longest same part in both of them. And then we have all the typing times. Here we are using some basic statistics. Actually, it's a t-test, but I'm not going into details here. Then we merge all of those numbers, and what we are left with is one number telling us the distance between 2 devices, or 2 profiles, to be more precise. Now into some results. We asked our users, we have several users, so far I think 5 different users, and from 5 to 10 profiles for each of them. And we started comparing them between each other. And here is actually what we found. In the bottom part, in the blue dots, there are all the comparison of the 2 profiles of the same user. It's not always the same user, but it's 2 profiles of 1 user. And you can see that the distances between them are kind of lower, around 5 usually. Up there in the orange dots, we can see a comparison of 2 different profiles, like 2 profiles of 2 different people. And you can see that the distances are pretty higher. So there is a way to draw some kind of line to tell, okay, if you are under this threshold, then you are the same. If you are over, then you are different, right? Actually, we opened up a Telnet server in our infrastructure. We opened the port 23 to the internet, and we are sniffing the traffic for the past, I believe, 3 or 4 weeks. And the tool can also give you some statistics of what is going on your device. Here you can see the number of unique IP addresses per 24 hours that are trying to connect to our device. You can see that there is around 150 unique IP addresses connecting to port 23 every day, every 24 hours. Out of all those IP addresses. There is around 50 IP addresses that can speak the Telnet. You will send them some Telnet negotiation bytes, as I mentioned at the beginning, and they will answer you some negotiation bytes. They can speak Telnet, but they do not brute force. They do not try to log in. The IP addresses that are trying to log in is around 20, 30 per day, and they are brute forcing. And I truly mean brute forcing. Most of them are brute forcing all the time, over and over and over and over again. Based on the profiles that we built of all those unique IP addresses, we discovered that, well, actually most of them are based on Mirai. So there is some kind of list of usernames that they are trying over and over and over again. To finish my presentation, I want to tell everyone that it is possible to detect attackers or bots on your behavior, actually, on the behavior of the bot. And you can even distinguish which bot or which attacker it is. We also know that the protection of IoT devices is pretty bad, let's be honest. There is nobody really doing anything about it. And we know it can be done better. And we need to do it better. Because if there's one thing about cybersecurity, then it is that the cybersecurity is a shared responsibility. And the more system we all secure, the more secure we all are. And that is what I would like all of you to take out of this, my short talk. Thank you very much.
Thank you very much. Can we jump to questions, please?
Black cat has a different owner, so the black cat should go to its owner to be fed.
All right. Do we have any questions here?
Yeah, we have here. Yep. Well, yeah, SSH is kind of tricky in here because SSH is encrypted, so you cannot read the commands from the network. We don't work in the device itself. Our tool works somewhere in the middle of two devices. And from reading the SSH, you cannot extract as many features as we can extract in here. But it would be definitely interesting to try it with SSH, at least the part of the timings, because the bytes are sent actually the same way. You just cannot read them, so that's kind of tricky. But we would have to try it. But it's a nice point for the future work.
All right, anybody has more questions? Yes?
Klidě. Mm-hmm. Chápu. I will translate the question to English. Okay, so the question is how we can make sure that the attacker is not going to attack the tool itself and the creation of the profiles and make himself look like somebody else on purpose, let's say. Well, this is tricky because we actually cannot. But right now we are in the situation where all the bots that we can see in the network are pretty simple and I would say stupid, but that's probably not the best word. They are actually copy-pasting the data. They don't really care about any typing. So if you are a human being, you are typing, and we can see that you are typing. So you are a human being. But any bot is just sending the commands. One packet, one command. That's it.
Okay, so we have two more questions here. What devices are behind Telnet?
I'm not sure if I understand the question. Like, Telnet is a protocol. It's still used, which is kind of weird. Well, mostly the IoT devices, the cheap IoT devices, I would say. Because To implement any encryption, you need a little bit better hardware, and when you are buying the cheapest of the cheapest IoT device that you can get, usually coming from China, they don't really care about any encryption. So they use the simplest thing we have, and that is the Telnet.
So I think that also answers the first question, why do they use that and what devices are behind? So what about disabling Telnet? Can you even talk to your devices then?
Well, if you disable the Telnet, then the device is not going to be accessible from the internet. And nowadays, unfortunately, when you buy a new device and you connect it to your home network, the device will open the port in your home router by itself, and you don't even know about it if you don't disable this function. This is how it unfortunately works. So you take home some device that you buy on eBay, let's say, it will open its own port 23 and redirect all the traffic to itself, so it is accessible from the outside, and you don't even know about it. So we can definitely disable the Telnet, but I'm not sure if this is the best way how to do it, because people want to see what is going on at their homes when they have a camera there, you know.
All right. I think it was the last question. So thank you all for coming. Enjoy your lunch, and I will be back here with a mobile UX topic next. Thank you.
Thank you.